Hello friends, welcome to the channel Sky's the Limit. In this video we are going to discuss the another important concept of physics. Before moving to the actual concept, let us understand the basic laws. That is, first one is the Coulomb's law. What Coulomb's law states, it gives us the electric field due to the point charge. Okay, due to the point charge it will give us the electric field which is equal to kq divided by r square. So this is our electric field due to the point charge. Similarly, in case of magnetism, we have Biot-Savart's law which give us the magnetic field at a point due to the current element. So therefore, what is the expression we have? That the dB is equal to mu naught by 4 pi I dl sine theta by r square. So this is Biot-Savart's law. Similarly, in case of electric field, we have the Gauss law which gives us the electric field in the symmetric situations. In the case of symmetric situation, the Gauss law help us. So similarly, do we have any such law which will help us to find the magnetic field in the symmetric situations? Yes, of course we have it in magnetism, which is nothing but the Ampere's circuital law. So what this Ampere's circuital law says? Suppose you have here, these are the current carrying conductors. Suppose the current flowing through this conductor is I1 and flowing through this is I2 and from this is I3. Now what Ampere says is, he says us to choose the closed loop. It does not depend, we can choose the closed loop anywhere as we wish. Suppose I take the closed loop which encloses the current I1 and I2. I can also consider the rectangle which is again the closed loop. It does not depend on the shape, which is enclosing here I2 and I3. So what he says that since the current flowing through the conductor will produces the magnetic field around it, so at every point there is magnetic field. So here also there is magnetic field at this point and at this point. And he says us to see the length element. So what is here length at this point? This is dl, that is tangential. This is dl, this is dl. Okay, and this is dl. He said us to move along this circular path. Then we can move either in the clockwise or in the anti-clockwise direction. It depends on us. Now since we are moving like this, what he said us to take the integral of this magnetic field and the length element. He said us to take the dot product of magnetic field and the small length element. He said us to find now total dot product of B dot dl, and he reminded us to take the close integral. That means if you are taking the loop which is something like this, which is not closed, then Ampere's circuital law does not holds good. Okay, always it should be a closed loop. So this is a closed loop. Therefore, the closed loop of B dot dl is equal to mu naught times the current enclosed in that closed loop. Okay, so this is known as Ampere's circuital law. So what Ampere's circuital law says, the line integral of B dot dl for a closed curve enclosing an area is equal to mu naught times the net I through the area bounded by the curve. Okay, so this is your Ampere's circuital law. Hope you have understood where B is the magnetic field due to the current I1, I2 and I3. Now here you must be confused, or there is a question arising in your mind that since we have here currents, this is I1, I2 and this is our I3. The direction of current is here I1, here it will be I2 and here let us take it as I3. Since we have considered this loop, okay, and we are moving in a clockwise direction, right? Clockwise direction. So what it is, B dot dl is equals to mu naught I. Now since it is I enclosed, if I write here I enclosed, does it mean that at to this right hand side this I3 is included? No. Since the loop only encloses I1 and I2, we can write here mu naught of I1 plus I2. Now the question arises, we see here the current I1 is moving out, okay, out of the wire, whereas I2 is entering into the conductor. So therefore, now what, both entering and leaving will have the positive sign? No. So therefore, in order to understand the sign of this I1 and I2, you have to use the right hand thumb rule. Okay, so what right hand thumb rule is, you have to curl your fingers of right hand in such a way that, see, this is the direction, right? So you have to curl it like this. You have to curl it like this. When you curl your finger like this, your thumb will point downward, right? Your thumb is pointing downward. So therefore, this is the direction of current. This is the direction of current. Since your thumb is like this, okay, and your direction is in this way, and your thumb is pointing downward, so this is your direction of current. So therefore, your I2 is positive and I1 is negative. Hope you have understood how we write the Ampere circuital law. See here, in this right hand side we have mu naught I. That means only the enclosed current is included. Does it mean here the B which we are writing, it only involves I1 and I2? No. In the left hand side, both I1, I2 and I3 are included in such a way that the effect of I3 is cancelled out somehow. That means at some point it is positive and at some point it will be negative, some point positive, some point negative. As a result, the effect of I3 will get cancelled out. Similarly, we see the same case in case of Gauss laws. There also it is the Gauss law is again the charges enclosed in the loops, right? So therefore here also this is your Ampere circuital law. Suppose you consider this is your loop now. Now can you write the Ampere circuital law for this rectangular loop? For this rectangular loop you can write it is B dot dl is equals to, and suppose we are moving in this direction now. We are moving anti-clockwise. If we are moving anti-clockwise, you have to curl your fingers like this and your thumb will point upward. So therefore, this will be the direction of your current. So therefore, your mu naught into I3 is positive and minus I2. So this is your Ampere circuital law. This is how you have to write Ampere circuital law. If it includes a number of currents, then it depends on the loop what you have selected. Hope you have understood the Ampere circuital law.